So in our yesterday's class, we completed Werner's coordination theory. Werner's theory explains how complex compounds are formed. But don't explain stability of the complexes, magnetic property, colored properties, etc. To explain stability of complexes, Sidgwick proposed EAN concept, EAN rule. What is that EAN? EAN is nothing but effective atomic number. It is EAN rule, my dear. It is effective atomic number rule. Effective atomic number rule. This is EAN rule. Who proposed this? This was proposed by Sidgwick. For what purpose? To explain stability of complexes. Okay. How to explain this EAN, the stability of the complexes? So, my dear, in complexes, there should be central metal atom or ion. This metal atom has some Z value. That is D block element. It has some Z value. That is nothing but atomic number. But while forming complexes, it converts into respect to ion, either +1, +2, +3, etc. That means it loses some electrons to reach its oxidation stage. For example, +1 reach, loss of 1 electron. Loss of 2 electrons gives +2. Loss of 3 electrons gives +3. That means oxidation state is equal to loss of electrons. Here, oxidation state is equal to loss of electrons. That is positive oxidation state. Positive oxidation state is equal to loss of electrons. Next, after losing electrons, this metal gains electron pairs from ligands and form coordinate covalent bond. That means during formation of complexes, metal always accepts a pair of electrons from ligands. Okay, so here the number of coordinate covalent bonds present around the metal in complex is equal to coordinate number. The number of coordinate covalent bonds present around a metal ion is equal to coordination number. That is nothing but secondary valence. One ligand donates a pair of electrons to the metal atom. That means one coordinate covalent bond is equal to 2 electrons. That is gained by this metal atom. That means after losing electrons, metal gains electron pairs. Okay, that means those electrons entered in the outermost orbit of the metal. Therefore, number of electrons gained by metal during this metal or metal ion during this complex formation is equal to 2 into coordination number. Because one coordinate number is equal to 2 electrons. That is, one ligand can donate 2 electrons. That means number of coordinate covalent bonds is equal to 2 into number of electrons is equal to 2 into coordination number. That means there is atomic number Z for a metal. It is metal atom. Losing its electrons to get its oxidation state, that is the minus oxidation state. But after losing electrons, it gains electrons. That is 2 into coordination number of electrons are gained. All this gives number of electrons in metal atom or ion in the complex. In the complex. This is nothing but Z is nothing but number of electrons. Some electrons are lost and some electrons gained. Total gives number of electrons present in the metal ion. This is called as final number of electrons present in the metal during the formation of complex. This is called as effective atomic number. How to calculate effective atomic number? Effective atomic number is equal to atomic number of that element minus its positive oxygen state. You can take only magnitude plus 2 into coordination number. This is the formula used to calculate effective atomic number. Here Z is nothing but atomic number of metal, oxidation state, coordination number. No. How to explain this EAN value towards the stability? Give stability condition. Stability. If EAN value is equal to its nearest noble gas atomic number, then the complex is stable according to EAN rule. According to situation. That means if EAN value is equal to nearest atomic number of a noble gas, then it is stable. If not, that is unstable according to Sidgwick. But my dear, every complex is stable, but some are more stable, some are less stable. It is not going towards unstable. That's why if EAN is equal to its nearest noble gas atomic number, that follows Sidgwick rule, that is EAN rule. If it doesn't reaches to atomic number of nearest atomic number of noble gas, that doesn't follow Sidgwick rule. But that is both are stable, which follows EAN, which doesn't follow EAN. Follows EAN means equal to atomic EAN value is equal to nearest atomic number. Noble gas is nearest atomic number. Right? Nearest noble gas atomic number. That is follows it. If it is not equal to nearest noble gas atomic number, then it is considered as unfollow situation. So this is the way to explain coordination number, that is nothing but stability of the complexes. So finally, EAN is equal to formula atomic number of elements, metal plus its oxidation state, minus its oxidation state plus 2 into coordination. Now let us take some examples. Okay, let us take an example. Okay, for example, I'm taking NiCO4, nickel tetracarbonate. Is this complex follows EAN or not follows EAN? Let us discuss one by one. First of all, you should find out which is the central metal atom in the complex. That is, nickel is the central metal atom. Now calculate its oxidation state. Now nickel, its atomic number Z is equal to 28. Okay, I want to find out EAN value. How much is the EAN? We have the formula EAN is equal to atomic number of that element minus its oxidation state plus 2 into coordination number. Okay. Now, here, CO, carbon monoxide, 4 ligands. So, each ligand donates 1 electron to this. This is monodentate ligand set. So, that's why coordination number in this case is equal to 4. Atomic number Z of this metal is equal to 28. Now we want to find out this oxidation state. Okay, how to calculate this oxidation state? Our formula is nickel, just like our previous situation. We have to find out, let it be X. X is the oxidation state of nickel, plus 4 into. My dear, carbon monoxide is neutral ligand. That means overall CO has 0. Here, is there any charge on this metal ion complex? No charge. That is equal to 0. If there is charge, you can equalize that total value to the magnitude of the charge. Okay, which is equal to X is equal to 0, my dear. Therefore, here oxidation state of nickel is equal to 0. Let us take one more example. FeCN 6 times minus 4. It is negatively charged. Let us take what is the oxidation state of this iron. Let it be X. X plus 6 into cyanide, Cn minus, my dear. Each cyanide has minus 1 charge. 6 into minus 1 is equal to overall charge magnitude value minus 4. Therefore, X is equal to plus 2. Therefore, oxidation state of iron in this case is plus 2. Let us take one more example. CONH3 6 times plus 3. It is positively charged. Okay. So I want to find out cobalt oxidation state. Let it be X plus each ammonia. Ammonia is neutral and H3 is neutral. Therefore, 0. No oxidation state is equal to plus 3. Therefore, in this case, X is equal to 3. X is equal to plus 3 oxidation state. Let us take K3FeCN6, my dear. It is a complex. It is overall, the value is 0, not charge. Find out oxidation state of this iron. Let it be X. Therefore, 3 potassium, my dear. Each potassium has plus 1 charge. Plus X plus 6 into minus 1. Total overall value 0. Therefore, X is equal to plus 3. Clear? Arya and Shiva. It is the way to calculate oxidation state. Okay, na?
Okay, sir.
So now in NiCO4, what is the oxidation state of nickel? 0. Therefore, here oxidation state is equal to 0. Now apply EAN for that complex. EAN is equal to atomic number of nickel, that is 28, minus oxidation state 0, plus 2 into coordination number 4. Now 28 plus 8, which is equal to 36. 36 is the, tell me, krypton atomic number. It is atomic number of krypton, my dear. Krypton is nothing but noble gas.
Sir,
Therefore,
coordination number means number of ligands, sir.
no. Number of ligands, it is not correct exactly. It is the number of coordinate covalent bonds. Because one ligand sometimes donates 2 electrons. That is bidentate, tridentate, like that are there.
Okay.
Okay. Don't go for ligands. It is coordination number is nothing but number of coordinate covalent bonds around a metal atom.
So, once can you
In
explain?
particular, in its complex.
Sir, ఒకసారి coordination number ఎలా కనిపెట్టాలో explain.
I will explain while writing coordinate, that is nomenclature.
Okay, sir.
Okay. Now it is 36 krypton atomic number, my dear. That means effective atomic number reaches to nearest unit gas atomic number. Now this complex, what is that? NiCO4 follows EAN. Okay. Let us take one more example. What is that? FeCN6 minus 3, my dear. I want to find out EAN for this metal ion. EAN is equal to atomic number of metal atomic number, iron atomic number 26, my dear, minus oxidation state of iron. Tell me oxidation state of iron. I want to find out iron. X plus 6 into minus 1, cyanide is minus 1, is equal to minus 3. Therefore, X is equal to plus 3, correct? Now, oxidation state of iron is plus 3. Okay, you can use magnitude towards oxidation state. That is 26 minus 3 plus 6 into each, it is monodentate ligand, my dear. So 2 electrons. That is 26 minus 3, 23 plus 12. That is 35. Is 35 atomic number of noble gas, because 36 is krypton, 35 is not kryptonite. Okay, not equal to krypton atomic number. That means this complex not follows EAL. Clear? Follows and not follows situations. Do you have any doubt?
Yes.
Okay, it is about EAN, my dear. Next condition. Next topic, that is Nomenclature of coordination compounds. Nomenclature of coordination compounds. What is this nomenclature? Naming of complex compounds, my dear. How to write a name of a complex compound? It follows IUPAC rules based on IUPAC rules. That means in our organic chemistry, in your first year, no doubt, there is IUPAC rules to write the naming of organic compounds. Like that, here also, nomenclature, that is naming of complex compounds also follows some IUPAC rules for complex compounds. Those rules are different, no doubt. But some certain rules are designed by our international council. So we can follow the rules while writing the name of the complexes. Okay. What are those rules? Okay. Before entering into the rules, you should know how many types of complexes are there. Okay. See, my dear, I'm taking CO, NaH3 6 times Cl3. When it is dissolved in water, tell me the dissociation is inside the square bracket, break down into fractions or not? Tell me your side.
No, sir.
Is this box break down into respect to ions or not?
No, sir.
No. But outside Cl2, chlorines, ionizable or non-ionizable?
Ionizable.
Ionizable. That's why it is totally CONaH3 6 times plus 3 ion plus 3 Cl minus ions coming. Correct or wrong? It is already explained in our awareness coordination theory, my dear.
Yes, sir.
Okay, CONaH3 6 times plus 3. Like this. For example, see, my dear, this bracket part is nothing but coordination entity. Which is nothing but coordination entity. This coordination entity here is positively charged entity. Therefore, because our coordination entity in this case is positive ion, nothing but cation. Because of this, this complex is cationic complex. Clear? Our coordination entity is cation, that's why it is called as cationic complex. Next, one more. K4FeCN6, my dear. When it is dissolved in water, 4K plus ions plus total box ion, FeCN6 minus 4 ion. These ions. Our coordination, box ion is nothing but coordination entity. This is our coordination entity. Okay. This coordination entity is a negative ion. That is nothing but anion. Therefore, this complex is anionic complex. Clear? This is anionic complex. Next, let us take one more example. NiCO4. It is the water. When it is dissolved in water, not break down into any ions. No ions, my dear. That means this complex is neutral. Not positive, not negative. That's why this is called as neutral complex. This is considered as neutral complex. In all these cases, in our complex entity, how many metal ions are there? Tell me. Complex entity. This is complex entity. One metal ion. Here also one metal ion. Here also one metal ion. Am I correct or wrong?
Yes, sir.
In our complex entities, how many metal ions are there? Only one metal ion. That is why all these complexes are nothing but mononuclear complexes. Clear? Why it is called as mononuclear? So in these complexes, only one metal ion is there as the central metal atom or ion. Only one metal ion. Only you should consider complex entity. Don't go for outside. Okay, now in our complex entity, only one metal ion is there. Here also only one metal ion. Here also one metal ion. That is why these are called as mononuclear complexes. If it contains two metal ions, then it is polynuclear complexes. For example, I am taking CO, NH3, 4 times, Cr, Cn, 4 times. Just a minute. CO, NH3, 6 times plus 3. Cr, Cn 6 times minus 3, my dear. It is total overall complex set. It is cation, it is anion. It has both cation and anion as complex entities. But it contains, in this total complex, cobalt is one of the metals, chromium is another metal. That means this complex has two metal ions, two metals. That is why it is polynuclear complexes. But in our syllabus, only we have mononuclear complexes set. That's why I'm taking only mononuclear. Mononuclear means there is one box. There is one box. That box contains only one metal ion. Okay, within the box, only one metal ion is there. That should be considered as mononuclear complexes. So those mononuclear complexes are divided into 3 types. One is a cationic complex, anionic complex, and neutral complex. Okay. Now, in nomenclature, we can follow IUPAC rules. IUPAC, cationic complexes and neutral. Cationic and neutral complexes follows same rules. Okay. Cationic complexes and neutral complexes, same rules. Next, anionic complexes follows different rules. Okay, so cationic and neutral complexes similarly. While writing the names of the complexes, similar rules you can apply. But anionic complex a little bit different. So that's why you can follow cationic and neutral complexes have same rules, but anionic rules are different. What are those rules? We can decide. Okay. So clear. Next, my dear, while writing the name of the complex, you should know about ligand also. So what are different types of ligands are available? Okay, so based on different situations, we can classify ligands here. See here, about ligands. Listen carefully, this is important. About ligands. That means, what is ligand? Ligand is nothing but Lewis base, my dear, that can donate to electron pair to others. That means it can donate electron pair to central metal atom or ion. It can donate electron pair to central metal atom or ion, whatever it may be. That's why it is electron pair donor. No doubt it is Lewis base. That is simply here we call it as ligand. Okay. Now, no doubt ligand has a lone pair. It can donate electron pair to metal. Now, my dear, based on the situations, these ligands classification, first classification, my dear, based on charge on ligands, these can be classified as positive ligands, negative ligands, neutral ligands. Positive ligands are nothing but cationic ligands. Negative ligands are nothing but anionic ligands. It is neutral ligands. Okay now. So based on charge, ligands are three types: cationic ligands, anionic ligands, neutral ligands. Let us take examples. So cationic ligands, my dear, NO plus, NO plus, that is cationic. So this NO plus, we call it as, you should remember the name of this ligand, that is nitrosonium. Nitrosonium, that is the name of the complex. Nitrosodium. Okay, now that is cationic. Cationic ligands are very negligible, my dear. That is the best part. Next, anionic ligands. So no doubt, Cl minus, Br minus, next I minus, okay, Cn minus, like this number of ligands are there. Okay, so see, my dear, these ligands names, it is chloro, it is bromo, it is iodo, it is cyano. See, my dear, every anionic ligand name is ended with O or not. See here. This is the rule. While naming the anionic ligands, those names must be ended with O. Response, please.
Yes, sir.
Anionic ligands names are ended with O. Correcta? Clear? See, chloro is also called as chlorido. Chloro or chlorido. Both are acceptable. Bromo or bromido. Accepted. This is correct, this is correct. This is correct, this is correct. Anyone you can use. Iodido. Both can be used. Cyanido. Both are used, acceptable. In our books, mostly these are used. In our NCERT books, are those are Ido words are used. Anionic ligands. Anionic ligands names are ended with anionic ligand name ended with O. Anionic ligand name ended with O. But cationic names are ended with IUM. Here, name ended with IUM. Prefix IUM. Here, prefix O. But neutral ligands, my dear, these have individual words. Neutral ligands means no positive charge, no negative charge. Example, NH3. No plus, no minus. Nitrogen is the donor atom. Next, H2O. Oxygen is the donor atom. No positive, no negative. It has two lone pairs. My dear, is an atom having more than two electron pairs, more than one electron pair, it can donate only one electron pair. Okay, so actually here oxygen has two lone pairs of electrons, but it has a capability to donate only one electron pair. Don't go for others. That means one donor atom can donate only one electron. Here in H2O, what is the donor atom? Oxygen is the donor atom. Oxygen can donate only one electron pair, even though it has two lone pairs. It is okay. It is ammonia. It is water. Next, NH2, CH2, CH2, NH2. Here nitrogen. Here nitrogen. It is overall neutral end. See, my dear, in this ligand, two donor atoms are there. How many donor atoms? Two donor atoms. Both have lone pair of electrons. It can donate this one and this one also. That means even though it is a single ligand, it can form two donor atoms. It has two donor atoms. It can form two coordinate covalent bonds. One ligand gives two coordinate covalent bonds. Even though it has no charge, that's why it is neutral ligand. So These are some examples towards neutral ligands. See here. Here also here negative C2O4 minus 2. C2O4 minus 2. It is nothing but oxalato. C2O4 minus 2 oxalate. That is negative ligand. See here, ammonia. While writing name of ammonia in your complexes, ammonia name is ended with name is nothing but amine. Amine. See, my dear, spelling is also important. We can use double M. Don't write single M. Amine. Ammonia name is nothing but amine. Only NH3. Only while naming the ammonia NH3 molecule name, you can use a double M. Don't go amine like this. Don't write. It is a double amine. Next, name of H2O is aquo or aqua. Both are acceptable. Aquo or aqua. See here, it is nothing but ethylene, diamine. My dear, here only one M is used because it is not ammonia, it is diamine, ethylene diamine. Only while writing the name of ammonia, you can use double M. In other cases, single M. Ethylene diamine. Okay, now. So it is simply the symbol for this one is EN. We can use this as EN. EN is nothing but ethylene diamine. Ethylene diamine structure is this one. Okay, all these are based on charges and positive ligands, negative ligands, neutral ligands. Positive ligands names are ended with IUM, negative ligands names are ended with O, and neutral ligands have their individual names. So for in case of ammonia, amine, double M, water, there is aquo or aqua. So ethylene diamine, here only single M we can use. So these are the some examples. So you can follow your NCERT book. Lot of other examples also there, but everywhere these rules you can follow. Okay.
Yes, sir.
See here. See here. Base classification. Classification of ligands. We are in first classification based on charge, already completed. Second classification based on number of electron pairs donated by one species. One ligand. These can be classified as monodentate ligands, bidentate ligands, C, polydentate, tridentate, tetradentate like this are their boys, but overall it is polydentate ligands. Monodentate ligands, bidentate ligands, polydentate ligands. It is based on number of electron pairs donated by one ligand. One ligand can donate how many electron pairs? Based on that, see here. NH3, my dear. Already I told to you, only one donor atom can donate only one electron pair only. Therefore, it can donate only one electron pair. Cyanide ion. It can also donate only one electron pair. Next, Cl minus. Chlorine has 4 lone pairs, but can donate only one electron pair. A single donor atom can donate only one electron pair, even though it has more than one lone pair. Okay, OH minus oxygen has 3 lone pairs, but can donate only one electron pair. It is negative and hydroxido or hydroxo. The name is this one. Okay, that means it is neutral. All these are negative. NO, it can also donate only one electron pair. That means all these are monodentate ligands. All these are monodentate. Dentate means how many electron pairs donated by a single ligand. Only one electron pair, that's why it is monodentate. If two electron pairs donated, that is bidentate ligand. If three electron pairs, that is a tridentate. Four electron pairs, tetradentate, like that. Okay. Now it is monodentate. Next, once again, C double bond O minus, C double bond O minus. It is nothing but C2O4 minus 2. What is the name of this this ion and this ligand? Nothing but oxalato. Yes, just we completed oxalato. Here oxygen, it is the donor atom. It is the donor atom. Here one ligand has two donor atoms can donate two electron pairs to the metal atom. That's why it is bidentate. Okay, na? Oxalator is an example to bidentate. Both the donor atoms are same type or different type. Both are oxygens or not?
Yes, sir.
So that's why it is symmetric bidentate. Clear? Bidentate, and it is both the donor atoms are same. That's why it is called as symmetric bidentate. Next, once again, CH2, CH2, ethylene, diamine, NaH2, NaH2, my dear. It is lone pair, it is lone pair. It can donate, it can donate. Therefore, it is the single ligand, but can donate it two, it has two donor atoms. Donates, that's why it is also bidentate. Bidentate. Its name is ethylene diamine, shortcut. So both the donor atoms are nitrogen atoms, am I correct? Both the donor atoms are nitrogen atom in ethylene diamine. Is this symmetric or asymmetric?
Symmetric.
Symmetric. Symmetric bidentate. My dear, symmetric bidentate ligands are indicated with AA type because both the donor atoms are same. Okay, now
Yes,
it
yes,
is
sir.
also AA type. Symmetric bidentate ligand. Next, I am taking CH2 NH2. CH2. It is. I am taking COO minus minus. It is called as. It is nothing but our amino acid. Amino acid. So it is the first amino acid. So what is the name of this amino acid? Tell me. NaH2, CH2, COO minus. Glycine. The name of this amino acid is glycine. Because it is negatively charged one, it is glycinato. Okay, na? Because name is ended with O. Because it is negatively charged one. Clear? Na? Negative
Yes,
ligands
sir.
names are ended with O. Glycinato. Now, this oxygen is the donor atom, this nitrogen is the donor atom. Is this bidentate or monodentate?
Bidentate.
Bidentate. So both the donor atoms are same or different?
Difference.
Different. It is asymmetric. Bidentate. It is represented as AB type ligand. Both the donor atoms are not same. Correct? It is
Yes, sir.
AA. It is AA. It is AB type. Okay, na? So all these are examples to bidentate ligands. Similarly, oxalato bidentate ligand. Next, glyoxime. That is bidentate ligand. You can check your NCERT book. Number of examples are there. It is not possible to write all these examples here, but these are very, very important. Oxalato. Okay. Glycinato. It is glycinato only. Next, glyoxime. Glyoxymato. All those. There is also negative ligand. Okay. So monodentate. That means depending on donating tendency, if only one electron pair is donated, that is monodentate. If more than one electron pair is donated, there is either two or three. That is two is nothing but bidentate, three is nothing but tridentate. Like that. But our example, the best example is that is I'm taking EDTA, my dear. EDTA. Let us observe ED. Ethylene diamine tetraacetate. It is the name of EDTA, ethylene diamine tetraacetate. EDTA, that is the abbreviation for EDTA. Ethylene diamine tetraacetate. Next, now its structure ethylene diamine. You can write first of all ethylene diamine. CH2 single bond CH2 NH2, my dear. It is ethylene diamine. Okay. These four hydrogens are replaced with acetate ion. That is CH2 COO minus ion, CH2 COO minus ion, CH2 COO minus ion, CH2 COO minus ion. How many acetate groups are added here? 4 acetate groups. That's why tetraacetate. Ethylene diamine tetraacetate. See, my dear, here nitrogen has lone pair. This nitrogen has lone pair. This oxygen has 3 lone pairs. This oxygen has 3 lone pairs. Next, these oxygens also have 3 lone pairs. Okay, now. And now tell me how many donor atoms are available? Tell me. So a species that has a lone pair of electrons can donate electron pairs to others. Okay, now. So how many donor atoms? See, my dear. Also here,
6
2
and
oxygens are also, each oxygen has 2 lone pairs. No problem at all. These are also possible, but these cannot donate electron pairs to others in this case. Okay. So because these two are identical, it is in resonance. Overall, this oxygen, both are identical. And you can choose only one. Okay. Resonance,
This is 6
there
and
exists. See, this can donate. This can donate. Here, out of 3, only one can donate. Here also one can donate. Here one can donate. Here one can donate. How many donor atoms?
6 is
6 donor atoms. Is there any positive or negative charge?
negative charge in for 4.
Yes, negative charge is there. How much
Oxygen.
negative charge? How much negative charge? Total
Minus
overall
4.
value? Minus?
Minus 4.
Minus 4. It is EDTA minus 4, my dear. Okay, now. This is, we write it as, we can written as EDTA minus 4. EDTA minus 4. It is hexadentate, my dear. Hexadentate. Okay, now. Clear?
Yes, sir. Yes, sir.
That means 6 ammonias are replaced with 1 EDTA. Am I correct? 6 ammonias, each one more EDTA. All those are replaced with only 1 EDTA. 1 EDTA is equal to 6 ammonias.
Yes, sir.
Because, okay, na, it is a density is 6 and density is 6. Clear?
Clear, sir.
Next. I'm writing this H as replaced with H plus. That is, it is converted to OH minus. This OH group doesn't donate electron pair to others. Now how many?
5.
Now how many? 5 only. Charge please.
3, sir.
3. That is EDTA minus 3L. Okay. EDTA minus 3 means one hydrogen is there. This is sometimes replaced with HEDTA because this is additional H. Okay. So it
Yes,
is hexadentate or pentadentate?
Pentadentate.
Pentadentate. Okay. If this one is also replaced with hydrogen, now it is H2EDTA minus 2, correct?
Yes, sir.
Or sometimes EDTA minus 2. Both are same end. Here also HEDTA minus 3 or EDTA 3. Mostly we can use this one. Here we can use this one. Okay. It is pentadentate or tetradentate. Is this donated or not? not possible. That OH. So overall, it is tetradentate or pentadentate or hexadentate. Tetradentate. That means, my dear, EDTA minus 4, hexadentate, EDTA minus 3, pentadentate, EDTA minus 2, tetradentate. Okay, na? Only these three only these three can be possible. From EDTA, 3 to 1 is not possible. 3 to 1 is not possible. Clear? It is polydentate. All these are polydentate ligands.
Yes, sir.
All these are polydentate ligands. See, my dear, sometimes the word diethylene triamine is used. Diethylene triamine means diethylene. That is, there is CH2 groups, two types. It is diethylene. Clear? It is one ethylene. It is one ethylene. Next, triamine. Triamine means three nitrogen atoms. It is NH. This is NH2. This is NH2. This is donor atom. This is donor atom. This is donor atom. Is this positive, negative, or neutral? Is this positive, negative, or neutral?
Neutral, sir.
Neutral. So monodentate, bidentate, or tridentate?
So tridentate.
Tridentate. Okay, na? This is, we call it as di-EN, my dear. It is the shortest term. EN means ethylene diamine. Di-EN means diethylene triamine. Okay, na?
Yes, sir.
Di-EN. See here, what is the name of this one? CH2, CH2, 1. CH2, CH2, 2. CH2, CH2, 3. How many ethylene diamines? How many ethylene diamines? Shiva, Arya.
Sir,
How many ethylene diamines in this structure?
3.
3. 1, 2, 3. In between, it is NH. It is NH. It is NH2. It is NH2. This is lone pair. This is lone pair. This is lone pair. This is lone pair. And now, what is the name of this complex, my dear? What is the name of this complex?
Diethyl.
Hmm? Ethylene is how many? 1, 2, 3 ethylene.
3, sir. Triethylene tetran.
Triethylene.
Tetran.
Yes, tetraamine. Triethylene tetraamine. Okay, na? It is tri-EN is the shortcut. It is di-EN. EN. We know. Okay, na? Okay, it is.
Yes, sir.
It is tetradentate, correct? Tetradentate. 1, 2, 3, 4. 4 donor atoms. It is tetradentate. So depending on that situation, denticity you should identify. Clear? Okay, na?
Yes, sir.
Denticity identified or not? Denticity. That means a ligand can donate how many electron pairs from this side, from its side. That is denticity. Based on that, monodentate, bidentate, tridentate, like that are available. Those may be positive, negative, or negative, or neutral ligands. If it is positive, positive ligands, negative, negative ligands, neutral, neutral ligands. Okay, na?
Okay, sir.
Next, depending on the situations, some ligands we call it as ambidentate ligands. What is this ambidentate ligands? Ambidentate ligands, my dear. What are these ambidentate ligands? First of all, this ambidentate ligand, I'm taking CN minus. Is this monodentate or bidentate ligand? Tell me.
Sir, monodentate.
It is monodentate. That means it is always monodentate. Maybe, for example, if metal is there, carbon has lone pair, nitrogen has lone pair. Buddy. So it has two lone pairs, two atoms, both the atoms have lone pairs. Maybe this carbon donated or nitrogen can donate. Either of these two, only one can donate. Clear? There is a ligand. It has a tendency to donate electron pairs, both the atoms, but only one can donate. Only one can donate. Okay. For example, metal with cyanide. With the C, there should be a bond possible. Or metal with isocyanate. Nitrogen can also donate. Even though both are same, but here donor atom is carbon, here donor atom is nitrogen. But it is a cyanide, no doubt it. That means
Yes, sir.
both the atoms can donate, but only one can donate at the time. That type of ligands are called as ambidentate ligands. Okay, na?
Yes, sir.
For example, NO also, nitrogen, oxygen. Nitrogen can donate, oxygen can donate. Either of these two, only one can donate. It is also ambidentate ligand. CNO, ambidentate, CNO minus. Okay, na? CNS, ambidentate ligand. That means either nitrogen, oxygen, or carbon, nitrogen, sulfur. Okay, only one can donate body. These are nothing but ambidentate ligands. Okay, na? While writing name of these ligands in the complexes, here carbon is the donor atom. It is cyanido. C because it is nothing but carbon is the donor. It is cyanido. N represents nitrogen donor. We should mention the donor atom also. Okay, na? While writing the name of the complex, you
Yes,
should
sir.
mention whenever ambidentate ligands are there, you should mention the names of the donor atoms also. Because link between metal and carbon, metal and nitrogen are changed. Here the link between metal and carbon, here the link between metal and nitrogen. Links are changed. Because of this situation, linkage isomerism is possible. In isomerism, you can decide. Okay, now. Link between metal and ligand change, that is called as linkage isomerism. Whenever ambidentate ligands are there, there should be a linkage isomerism. Clear?
Yes, sir. Yes, sir. Clear, sir.
Next, ambidentate ligand. Next, flexidentate ligands. Flexidentate ligand. Flexidentate means, see my dear, it is SO4 minus 2. Okay, na? So here, this oxygen has 3 lone pairs, this oxygen has 3 lone pairs. It can donate this oxygen can donate, this oxygen can donate. Now tell me in this situation, what is the density of this SO4 minus 2? Density means
No, sir.
how many lone pairs are donated? Now it can act as a bidentate, correct?
Yes, sir.
Bidentate. Okay. Now in this situation, this is bidentate. But sometimes same SO4 minus 2, even though it has a capability to donate 2 electron pairs because it has 2 donor atoms, but only one can donate, but not other. Now in this case, it is monodentate. Correct? Na? In this case, it is monodentate body. That means our SO4 minus 2 sometimes behaves like bidentate, sometimes behaves like monodentate. That means it has flexibility. Not always bidentate, not always monodentate. Depending on the situation, it can adjust.
Yes, sir.
Depending on situations, it can adjust. That type of ligands are called as flexidentate. Okay, na? A polydentate ligand behaves like a monodentate as well as polydentate. Behaves as monodentate or polydentate. Clear?
Yes, sir.
Or, for example, 3 times or 4 times, it can be possible. For example, our EDTA is a flexidentating. Am I correct?
Yes, sir.
Sometimes 6, 5, 4. Okay, na? EDTA flexidentate. Or SO4 minus 2 flexidentate. Flexidentate means density is variable. Density is variable. That is called as flexidentate conditions. You can identify all these situations. Sometimes, my dear, see, my dears, in these all cases, electron pair, those atoms which have lone pair of electrons can donate electron pairs to the metal atom. In all these cases, what I just told to you, only lone pair of electrons are donated by the electron, that atoms. But see here, CH2 double bond CH2, my dear. Here pi bonded. These pi bonded electrons may also donate. It is possible. This is pi donor atoms. Pi donor atoms. Pi donor molecules. Okay, pi bonded. It can form pi bonded complexes. It can form pi bonded complexes. Clear? Not only lone pairs, the electrons present in the pi bonds may also donated by that ligands. That is called as pi bonded ligands. For example, see here. It is minus, my dear. Is this aromatic or not aromatic? Tell me. It is aromatic, no doubts. I don't have that much time to explain that. Okay,
Yes.
it is aromatic. Okay, cyclopentadienyl anion. Cyclopentadienyl anion. Okay, so now how many electrons? It is in resonance. Pi bond, lone pair. All these are in resonance. Here 6 electrons are in resonance. Okay, because based on this is we call it as we rewrite it as minus. Both are same. Am I correct? Both are same.
Yes,
That,
sir.
okay. This ring has 6 electrons. Am I correct? This ring has 6 electrons.
Mm.
Okay, 3 pi bonds, 3 parts, 3 bonds. We call it as 3 bonds. Okay, so that means here iron is here. Fe plus 2. This ring can donate like this one. Similarly, one more. Okay, this is donated to this one. Now, what is the coordination number of this Fe plus 2? Coordination number means how many electron pairs donated by, how many electron pairs accepted by that metal ion. How many electron pairs? Here 3. See, my dear, already I told to you 1, 2, 3. Here 3. Here 3. Total coordination number of this Fe plus 2 is 6. Am I correct or wrong?
Yes, sir.
Okay, na? So this complex is called as sandwich complex and it is a ferrocene. In ferrocene, Fe plus 2 is there. Fe plus 3 plus 2 is in sandwich between two cyclopentadienyl groups. Sandwich means, so just like this. Our pen is in sandwich between my 2 hands. Okay,
Yes,
na?
sir.
Like that. Okay. Here Fe plus 2 has coordination number 6 because total these three overall 6 electron pairs are accepted by the Fe plus 2. Here 5 bonded electrons are involved. This is called as pi complex. This is called as pi complex. Okay, na? Pi bonded complex. Like this is also possible. This is we call it as that is number of electrons. Here, how many carbons are there in the ring? While writing the name, you can identify, you can note down the number of carbons in the ring. This is while writing eta power 5n. Eta power, that is the ring complexes are there. If ring ligands are there, that number of that is while writing the pi bonded complex. So that ring name, the number of carbons present in the ring, we can represent it as eta power something. Eta power 5. It is always pi bonded complexes. While writing the pi complexes, so that is eta power. See here, it is eta power 2. Not only that, these 2 carbons are there in the pi complex formation. It is eta power 2. Okay, na? Clear? Eta power 2.
Yes, sir.
Eta. That means eta, the letter eta is used in case of pi bonded complexes. If pi electrons are involved, that eta is used. So number of carbons in the ring you can use it as that is a prefix or suffix. Not prefix, suffix, it is superscript. For superscript eta, that number of carbons are used. Clear? Whenever eta symbol is used, that is a pi bonded complex.
Yes, sir.
So in superscript, number of carbons in that ring or in that bonds in that compound are there. That is indicated. Clear? I have no doubt.
Yes, sir. Clear, sir.
Clear, sir.
Clear. Next. Now naming of the complexes. My dear, eta power, eta, that is called as hepticity. Hepticity. That is hepticity in ferrocene is 5. Okay, na? If C double CH2 double bond CH2 is there, their hepticity is 2, eta power 2, eta power 5. Power is there. That power is nothing but hepticity. Okay, na?
Yes, sir.
Okay, now naming it. Naming. While write the naming of the complexes, first of all, my dear, name cation first. Okay. Next, anion next. First, you can write the name of cation and then anion. Okay, na? Clear? Always you can write cation first. Okay. Next, my dear. Don't write the number of atoms. Don't write the number of atoms present outside of complex entity. That means within the box, outside the box, there should be are there. Some ions may be there. Don't write the number of ions. For example, there is K3FeCN6N. Outside bracket, how many potassium ions are there? 3 potassium ions. Don't write that number 3. Don't consider that. For example, CONH3 6 times, Cl3 are there. Okay, only you can choose chlorine. Don't choose that 3. Clear point of the Don't write number of atoms. Only you should consider atom. Don't consider that number of atoms while writing the name. Clear?
Okay, sir.
Next. First of all, cation first and then anion. Okay. I'm writing the rules for cationic and neutral complex. Rules for cationic and neutral complexes. Because cationic and neutral complexes follow same rules already I told to you. Okay. See here. I'm taking cationic. Cationic complex means our box ion is positive. Our box ion, that is complex entity, is positive. See here, CO, NH3, 6 times Cl3 Okay. In this case, this box has positive charge, this chlorine has negative charge. Our box ion is positive or negative? Tell me. It is +3 and that is -1. Our box has positive or negative? Positive charge. It is cationic complex. Already I told you. Cationic complex. So while writing the name of the complex, so you should write cation first and then anion. So now I'm writing cation. Now cationic complex cation is Here cation is complex ion. While writing the name of the complex ion, either it is cationic or anionic, whatever it be. So if you want to write the box ion name, first mention ligand first, then metal. If more than one ligands are there, follow alphabetical order. Okay. See, my dear, if NH3 is there, what is the name of this compound? This ligand? Amine, double M. If H2O is there, what is the name? Aqua. Okay. So if both ammonia and water both are there in the complex, which one write first? Amine starts with A. Aqua starts with A. First letter we cancel. Next, M and Q. Which one is first comes out? Which one? M or Q? In your alphabets. Are you there
Sir?
or not?
Yes, sir.
M and Q. Among these two, which one comes out in your alphabets?
Yes, sir.
M, Q లో ఏది ఫస్ట్ వస్తుంది
MS,
ఆల్ఫాబెట్స్ లో?
sir.
M, sir. M, sir.
M,
MS, sir.
M.
Yes,
That's
sir.
why first you write ammonia and then aqua. You can follow alphabetical order. See here, what is the name of this complex? See, first you should write cation. Cation is the box ion. While writing the box ion, first to ligand and then metal. How many ligands you should mention? How many? 6. That is hexa. Okay. Ammonia. What is the name of ammonia? Amine. AMMNE. You should write double M, my dear. Ammonia is there. Hexaamine. Cobalt is the metal.
Cobalt 2.
Cobalt. You can write within the parenthesis the oxidation state of that cobalt. Here, cobalt oxidation state is a +3, my dear. Already we calculated in our previous class, previous topic. Say it is a +3. That should be mentioned in Roman letters. Hexaamine, cobalt 3. Always metal name followed with oxidation number in Roman letters. Okay, completed up to this. This is cation part completed. Now, while writing outside the ions, don't mention the number. Only you can identify what is that ion is there. That is a normal case. It is a chloride ion because it is not inside the bracket. It is outside the bracket. Ordinary ion. So Cl outside. Ordinary ion. That is chloride. Not trichloride. It is just chloride. Hexaamine, cobalt 3, chloride is the name of this complex. Now one more. Let us take an example.
సార్ మరి బ్రౌన్
See,
కాంప్లెక్స్ కి అక్కడ 1 పెట్టారా సార్?
one better. Cr, H2O 3 times, NH3 3 times, Br3. It is the complex fire. It is the complex. Now write down there. Now here complex is a positive complex entity. It is a negative. Is this cationic complex or anionic complex? Tell me. Cationic complex or anionic complex? Tell me first of all. The taking complex.
Cationic.
Because box ion is cation, that should be cationic complex. Okay. While writing the box ion, first of all, you should mention cationic. So names the first note cheyalsini cationic name. Because you can write first cation name and then anion name. Okay, na? So cation name, cation is the box ion. While writing the box ion, first you should write ligands and then metal ion. So it is aqua or aquo. It is amine, AMMINE. Among these two, which one comes from first? You can follow alphabet. First A and A, both are same. That's why it is not possible which one is comes
Amine,
out
sir.
first, first letter. Now Q and M. Among these two, which one comes out first? M or Q?
M, sir.
M, that is why. It is how many ammonias are there? 3. Triamine, triamine, it is completed. Water, 3 water molecules. Triaquo or aqua, whatever it may be, it is completed. It is chromium. CHROMIUM, chromium. What is the oxygen state? It is 3 ending. Calculate yourself. Chromium oxygen state 3. So it is completed. Now outside the bracket, don't write the number. Which one is the present? Bromine. Bromine is nothing but bromide. Bromide. It is the name of this complex. Triamine, triaquo, chromium 3, bromide. Okay, na?
Okay.
Yes, sir.
Sir,
Now,
doubt on sir.
NiCO4, just a minute, Shiva. Or Arya. NiCO4, is this neutral complex, positive complex, or negative complex?
Neutral, sir.
Neutral. Neutral follows cationic rules or not?
Yes, sir.
Okay, while writing the box, first you mention ligand, after that metal. How many ligands are there? 4 ligands. Tetra, cobalt, carbon monoxide. The name is carbonyl. Okay, na? Wherever CO is there, you should write the name carbonyl. That is also neutral element. Carbonyl, completed up to this. Nickel, oxygen state 0, my dear. This is the end of this thing. Tetracarbonyl nickel 0 is the name of that complex. Okay.
Yes, sir.
Okay.
See here. This is cationic complexes and neutral complex. Now anionic complexes. For anionic complexes, no doubt, all are regularly metal name ended with AT as suffix. Metal name is ended with AT. Next, if metal has Latin word, that should be used. If metal has Latin word, for example, generally Cu we call it as copper. Am I correct?
Yes, sir.
Commonly we can call it as copper. Cu as
Yes,
copper,
sir.
but in Latin word it is cuprum. Correct?
Yes,
Yes,
sir.
sir.
Cuprum or copper actual name?
Cuprum,
Cuprum,
sir.
sir.
Cuprum. You can use only cuprum, but not copper. Okay, na?
Okay,
Yes,
sir.
sir. Yes,
Iron
sir.
is there. Iron is, it is common name is iron. We generally call it as iron. But actually it is ferrum. Am I correct? Latin word is ferrum.
Yes, sir.
So that's why here we can use ferrum only. Don't use iron. So in anionic complexes, Latin words must be used, but not in cationic complexes and neutral. In case of cationic, iron 1, iron 2 can use. But in case of anionic complexes, don't use the word iron. It should be ferrum. Okay, na? So along
Yes, sir.
that word is ended with AT. Ferrate, cuprate. Okay, na? AT. Let us take an example. K4FeCN6, my dear. Okay, it is a complex. In this complex, this is positive part, this is negative part. While writing the names, you should write first positive part. And it is complex ion or ordinary ion, you can follow no doubt. Okay, na? So here, cation is a normal ion or complex ion? Is this normal ion or complex ion? Okay.
Normal.
Tell me,
K
please.
normal.
Normal ion. So normal ion's number is not mentioned, correct or wrong?
Yes, sir.
So it is just potassium. Okay, now potassium. That is normal ion completed. Now it is box ion, anion. You can follow anionic rules. Okay, box. While writing the box, you should mention first ligand and then metal. Okay, ligands. How many ligands are there? 6 ligands. What are those ligands? CN. CN name is cyanido or cyano. Am I correct? Now, hexa cyanido. or sometimes cyano. Both are acceptable. Hexacyano or hexacyanido. Okay, it is completed. Now iron. So it is anionic complex or cationic complex?
Anionic complex.
Anionic complex names, metal names must be Latin. If Latin word is there,
Ferrate.
you should use Latin. Here, ferrum or iron, you can use.
Ferrum, sir.
Ferrum.
Ferrum. It is a ferrum. Next. Because metal name here must end it with ATN. Ferrate. Okay, na?
సార్ ఇక్కడ
Ferrate.
మనం ఆక్సిడేషన్ నెంబర్ చూపించకూడదా సార్?
Just a minute, just a minute. After that, within the parenthesis, you should write the oxidation stage of that metal. Here, oxidation state of iron is, see my dear, 4 potassium, 4 into plus 1, iron I don't know, plus X, plus 6 into minus 1, overall value is 0. Therefore, X is equal to plus 2, correct?
Yes, sir.
Now it is
Yes, sir.
Roman letter 2. You should write the name. After that, after ATE, within parentheses, you should write the oxidation state also. Clear?
Clear, sir.
Yes,
Okay.
sir.
Next. For example, my dear, if between metals, if there is a bridged ligand, we can use mu, the word mu hydroxide. We can use mu. Mu indicate that ligand is in bridge position. Okay, na? Everything is common, but that ligand is bridge position. Bridged ligands are indicated with mu. Bridged ligands are indicated with mu. Okay, na? Like that.
Yes, sir.
So now